All right, so we're just gonna go through the what you just finished up. This was homework for my other classes, but you guys just didn't have to do it last night. So we're gonna start with the sediment size. So again, remember, all you have to do is look at the dotted line. For example, clay, they do not give you a starting number, but they tell you the biggest piece is 0.0004. What did you say for this? For the other part, because it did ask for a size range. What did you say the smallest could be?
The bottom line.
The bottom line, which is labeled what? Okay, what I want to point out is it's not labeled 0. So it is labeled 0.0001. So if you did say 0 to 0.0004, just fix that so it does say the 0.0001. And then just going up, clay 0.000, I'm sorry, silt 0.004 to 0.006, 0.006 to 0.2, 0.2 to 6.4, 6.4 to 25.6. And then for boulders, I did say 25.6 and I just put plus. It could just be anything greater, or if you did top it off at 100, that's fine too. With these, all you had to do was find what they gave you. The first one was 200 centimeters per second. So here's 100. Where's 200? That was actually a question. The next line over. We're used to these starting points being zeros. So thinking that this would be 0 and that would be 100, then 200, but this is 100. 200 is the next line over. Now notice they did also give you the little marks at the top as well. So there's the 200 line. The reason they did that is because then you can make a really nice straight line. And where does 200 and the graph line hit? I said right here at 25.6. If you said something different, I don't think the 6.4 one. I think that you can see when I put the straight edge, the 6.4 is a little before the 200. So I did go with 25.6. I had 0.2 for number 3 and 0.006 for the next one down. Now the next one, they give you the sediment size. So you start at 10. Go over till you hit the line, read down. Now that one is also kind of hard to see. I went with, it was a little less than 200, and so I went with 150, but if you put 200, you're fine. Did anybody put something drastically different? Anybody not sure if your answer is good enough? And then finally got 5, and then the last one isn't quite on here, but it is in this little reading. It says this generalized graph shows the water velocity needed to maintain but not start the movement. Variations occur due to particle density and shape. So what does it mean this is the water velocity needed to maintain? So how much energy is needed to start the movement? Have you guys ever tried to push a car when it's in neutral? When you try to push a car when it's in neutral, how feels light. It feels lighter than it should, that's for sure. But is it easier to keep it going or to get it started, or are they the same? It's easier to keep it going. It's takes a little bit effort to get it moving, but then once it's moving, it's actually not super bad to keep it moving. So that it's the same here. You do need a little bit more energy to start moving the rocks, but once they're moving, this graph will tell you how much energy is needed. So there is more energy. I circled the wrong one. It is less energy to keep it going. More energy to get it starting. And then less energy to keep it going. Sorry, I didn't read carefully. So it's harder to get something moving, but once it's moving, it doesn't take as much energy. How much energy is needed to start a particle moving in a stream? Yeah, you're right. I did it right the first time. Holy cow. Yeah, it's more than is required to keep it going. So remember when Rayleigh said I seem out of it? That's because I haven't had enough coffee yet today. Not that this is coffee, but maybe water will help. All right. No one drinks 40 ounces of coffee. This is just a water cup. You would? Your homework is the questions. There are 13 of them. Don't skip number 7 just because it's not multiple choice. Do question 7 as well. So we'll check those tomorrow. In the meantime, I needed you to, I guess I should have, no, we don't need it. Turn your packet to page.
So we're not doing this.
Do what?
Homework?
No, you gotta do class before you can do your homework. I stream, you stream on page 25.
Man. What?
All right, so moving on. We have our very final thing we need to learn for this chapter, and then we're going to move on. It is the final part of chapter 5. I think it's going to take the rest of today and maybe even into tomorrow to finish this up, but we're on page 25. And it's I stream, you stream. See what I did there? Pretty funny, right? Right? All right. Aha. Running water is the primary agent of erosion on Earth. Most running water is found in streams or rivers. There are a number of factors that affect the movement of sediments in a stream. Any running water forms a stream. Gradient, discharge, and channel shape influence a stream's velocity, erosion, and deposition of sediments. Sediments transported by a stream tend to become rounded as a result of abrasion. Stream features include V-shaped valleys, deltas, floodplains, and meanders. A watershed is the area drained by a stream and its tributaries. I actually want to go back to this paragraph for a second. The very first sentence is something I want you guys to reread and figure out what that means.
I don't know what that is.
Chapter 5 chapter, we've been working on for a couple of weeks here. What does that very first sentence mean? Running water is the primary agent of erosion on Earth. What does primary mean? First, number one. So what does it mean that running water is the number one agent of erosion on Earth? It's the most abundant. It's the most, not necessarily most important, most abundant. It's the number one agent of erosion. Meaning right now, or any 24 hours a day, 7 days a week, running water is the one doing the most erosion around the world at any given time. Why is that?
Probably because we have oceans.
Well, not oceans, but we have rivers. Anytime running water is moving, all the streams, all the rivers, all the creeks, all the everything, there's running water erosion. So right now, running water erosion is the one that's happening the most. Why not glaciers? Okay, they are slow and no. How many glaciers we got around here today? Barely any. So very few glaciers exist right now. So even though glaciers created almost all of New York State's landscape region, it's not happening today. So the fact that running water is happening today makes it the number one agent of erosion. So keep in mind, New York State was created by glaciers. All right, next part, we're gonna talk about gradients. So the average velocity or speed of a stream depends on stream discharge and gradient. Stream discharge is the amount of water in a stream. Gradient is the steepness of the slope down which the stream is flowing. There is a direct relationship between the discharge and or gradient and the velocity of a stream. As either discharge or gradient increase, the velocity of the stream increases. A typical stream may vary greatly in slope between its source, which is the head of, and the mouth where it empties into a lake or a stream. Therefore, it may flow at different speeds at different places. At times near the mouth of the river where the slope is small, the velocity may still be great if the discharge is great. what I need you to do below is, given the data table below, calculate the gradient between the indicated points. We're going to get rid of this use the scale part. So we have to find the gradient of this stream. What stream you have? It's the Ritz River, and it's over here on the floor.
Sorry.
So here's the Ritz River over here on the floor. So what I need you to do is bring your pockets and your body this way. So I do have a copy of the Ritz River here on the board, but we're also going to be using this Ritz River here on the floor. It's the same river. So we need to calculate gradient. Who remembers how to calculate gradient? You do? How do we calculate gradient? First of all, what is gradient? It's the slope. It's how steep the slope is. Anytime we calculated anything in this class, where did we look? Front page of the reference table, luckily. Brennan said this here. Brennan,
Yeah, you're supposed to collect that benchmark.
no, put this in the first ACE book over there. Yeah, I don't care. Brennan said this reference table right here. Do we wanna look at this morning?
No, oh, I will.
Too late. Alyssa, what is the formula for gradient?
Couldn't tell you.
Change in field value over distance. I believe there is a spot in your notes for that.
If you ever take my paper.
Right here, formula for gradient. Plug that into your paper or your. So it's the change in field value divided by distance. Yeah, it definitely did not give you enough room. Yep, right there, Bert. So the formula is change in field value divided by distance. Who remembers what the half field value is? We did this back in chapter 2. This should not be news to you. What is change in field value? Okay, it's the change. It's the change in the elevation. So I provided some measurements on your packet there. And it says that point A on this map is 500 meters above sea level. Point B is 427 meters above sea level. C is 378 meters above sea level. D is 218. And E is 106 meters above sea level. So how would we find the change in field value between points B and D? You just subtract them. So again, what was the elevation at B?
427.
427. What about C? Or sorry, what about D? 218. James is in charge of the calculator. I do, trust me, James.
I would.
All right, so James did the change. And again, how did James do the change? Someone in the back, tell me what he did to get that number. How do we get the change? Subtract. So B was 427. D, 218. And when you subtract that, you get 209. We need to still find the distance. How will we find the distance? What did you say? The scale thingy. The scale thingy on the bottom of the paper. So how are we gonna do this? We're gonna go from B to D.
You don't. Oh, you probably curve around the inside of the stream right there.
Why do we have to curve? Because we can't go straight. How are we gonna curve around the stream? How would you measure it?
With the wall.
With the wall? How do you, seriously though, how are we going?
You go point to point.
Point to point?
Yeah.
Diagonal?
Nope, let me tell
No, does it go diagonal?
you.
So like that? Is that the distance between B and B?
Oh,
No.
You got it.
You go diagonal. Well, we only want to go from B to D. with this.
Yeah, there's no A in that.
Yeah, we're just going B to D. It is.
Oh, yeah, then,
This is good. This is the distance from C to D. But we mean from B to C to D.
gotcha.
So alright, calculate. Now, I'm actually gonna get rid of the ruler. Now, on a reason, you're not gonna have the ruler, but you are going to have a straight edge. So how can we do this with just a sheet of paper?
Oh, yeah, you said something.
Somebody help us.
Oh,
Yeah,
because I grew up Chevrolet.
okay. So notice how Alyssa is going on an angle from B to C, then what? Then she uses the mark from C as her starting point. Oh, man.
Oh.
Yeah, well,
Oh,
perfect. This is something that I have seen needing to be done on the regions before. Thanks, Alyssa, I appreciate it. You do, if there's ever a curvy thing that you have to measure the distance for, Alyssa just did it perfectly. Went on an angle as best she could from B to C, then turned the paper to go on that angle from C to D. So we will not, but ideally a piece of string probably would have made life easier, but you won't have that on the regions. You'll only have this straight sheet of paper. Now what do we do with those two marks? All right, go for it, Logan.
Oh, okay.
No, do it, Logan. Go.
So you go about, here, there. I'd say it's about 7.
Okay, so from the 0, we land right around the 7. I agree with that. So we have the distance between B and D is 7 kilometers. So again, how do we find the gradient?
Okay.
Well, we already subtracted to get the change. We got the 209. Now we divide 209 by 7. James, you're still in charge of here. 209 divided by 7. Okay, so James got a really big number.
You're right.
29.857,142. I'm going to remind you that unless they tell you otherwise, in science, you always go to the 10th place. Which number is the 10th place? The 8. But what happens with the 8? Do I just leave it like that?
Goes up to 9.
Why does it go up to 9?
5 is higher than 4.
Right, so 5, the 5 here tells you to round up. So this is 29.9. What are the units?
Meters.
Meters over kilometers, which means meters per kilometer. So that's calculating the gradient. This will be required for you to know how to do this on a screen. We'll say the next part. So the next question is from A to E prime.
Yeah.
I'm gonna save that one for you. We're gonna move on to the back, to the next page. This is the absolute final thing you need for this chapter. I will tell you this shows up on the regions every single year. There was at least 5 questions about this on the regions that the kids just took last week for the January test. Here's the next part. So I do recommend paying attention. It says channel shape and velocity. The position of maximum velocity in a stream cross-section varies with changes in the direction of the stream flow. The velocity of the stream is generally greatest just beneath the surface near the center of the channel, where there is less friction with the banks of the river and the atmosphere. Water near the outside of a curve has a greater velocity of water than on the inside of a curve. Therefore, erosion takes place on the outside of a curve and deposition on the inside. On the five cross sections, oh my goodness. On the stream, 5 cross sections are marked. In the boxes below, draw what each might look like. Are the bottoms even? Is one side deeper than the other? So what we have to do is draw what the stream would look like if you hopped into the water and walked across from A over to A prime. Meaning we need to know what the ground, what the stream bottom looks like. So let me kind of explain what we've got going on here. Here is the surface, this up here. Whoa, I guess I forgot the body of my stick person. There we go. This is the bank. That is the top. And you're going to walk in. And what happens when you walk into a stream? It gets deeper. You get wet. It gets deeper. It gets deeper. Then what? Does it just keep getting deeper?
So there's a bank.
Then you start going up the other side. That bank's not going to be even on both sides of the river, and it depends on where you are in the river. So let's take a look at A, walking over to A prime. Take a look at that area. What do you notice about A to A prime?
Parallel.
They are parallel to each other, I'll give you that. But what else do you notice? Where is A? Where is A prime? On a meander, that's what I'm going for. It's on a curve. It's not a straightaway. They are across from each other, that was on purpose. But it's on a curve. That's the kicker. So if you start, if the water is flowing from over this way toward, so it's going from A to E. Okay, so my question is, what do we know about the outside and the inside of the curve then? Oh, the outside goes faster. So this is going faster on the outside. What is happening more on the outside?
Erosion.
More erosion. And when there's more erosion happening, what's it doing to the bottom of the stream?
Pushing it.
It's moving the sediment, it's pushing them or pulling them or taking them away. Either way you want to think of it. It's digging the sediment out on A prime. What's happening to A though? Water's slower there. What happens when water goes slower? The sediments get dropped off. So what will the bottom of the bank look like there?
Bigger rocks.
Okay, they'll have bigger rocks getting piled up there. So if we were to get in the water at A and walk across to A prime, where is it going to be deeper? A prime. And we need to show that on here. So we're really going to draw what the bottom of this river looks like. And Rayleigh answered the question perfectly. I asked, where is it going to be deeper? And it's going to be deeper over towards A prime. So what I want you to do is put a dot at the bottom here to indicate the deepest spot of this river. It's over towards A prime.
Okay.
Now we're going to draw the bottom. So if we got in at A and walked over to A prime, the first part of our walk is going to look something like that. Once we get to the deepest spot, then we're going to start to go up. What do you notice about the two different sides of the stream? One side is steeper, one side is more gentle. The steeper side is on A prime. Why is the steeper side over by A prime? Because that's where the erosion's happening. Sediments are getting piled up by A and being taken away by A prime. This should be what your paper looks like. So we need that exaggerated, gentle side on A, the steeper side on A prime. Now let's take a look at B to B prime. What do you see going on there?
Straight across from each other.
They are straight across from each other, just like A and A prime were.
Oh.
But it's a straightaway. Okay, it's a straightaway. It's not on a, B to B prime. So with a straightaway, where is the deepest part going to be? In the dead smack center, good. So you're gonna do the same idea, but the dot where the deepest spot is going to be located. So in other words, I don't know why B prime got moved here. It was supposed to be on the edge. If you wanted to move that over, go ahead. So again, with B to B prime, the deepest spot is in the center. And when you get in, both sides will look the same. What's happening at C to C prime?
Across from each other.
Okay, we've established they're all across from each other.
It's a curve,
It's a curve.
but C is the outside of it.
So C is the outside of the curve this time. So what does that mean about C?
It's gonna be the deepest.
C is going to be deeper. So how do we go about drawing this?
Put the dot closer to the D,
Put a dot closer to the C this time.
and C will be deeper, and then the other one will be.
So C, the dot gets closer to C.
And then C will be deeper, and then the other.
Yep, C to C prime. All right, you have 5 minutes. I want you to go ahead and finish the next two. Finish B. Look up figure out what the bottom would look like from B to D prime and E to E prime. Again, you do have homework.
Can you switch it to?
You have homework again tonight. It is those multiple choice Regents questions. So we have time to go over these at the end, so people out after you draw them on, see how they come. So don't worry.
Oh, my lord. Take it? Oh, you guys can call me an academic, but. Yep, don't look at my picture, thank you. Oh,
But now I have no idea what you got going on. D to D prime, where's the deepest spot going to be? In the middle. Why is it in the middle?
What?
Because it's a straightaway. And then how about E to E prime? E to E prime. It's gonna be deeper by which one did you say? E prime. Why is it deeper by E prime? Outside of the curve, thank you. So that means it's gonna look like this. Guys, when you're drawing these, make sure you have that exaggerated, way more gentle on one side, way more steep on the other if it's on a curve. Don't make me get out a ruler and figure out the angles you got going on. Make it obvious. We are going to stop there. We still have to do question 2 on the front and this bottom part here tomorrow. But we are officially, I guess technically we still have this to do tomorrow, but it'll take 5 seconds. And we are officially done with the chapter. You do have homework. It is, we already did the front of this handout. You're doing the 13 Regents questions attached to it.
Yeah.